diodes right now. We're done with op amps. Any questions at all? All right. The whole thing with a diode is it's either on or it's off for the ideal case. Now there is going to be some we'll get to the non-ideal diode. It's been a while since I'm going to go through a couple of problems and questions about these diodes to see what you what do you think of this?
Jump over the bushes. Yeah. Oh. Yeah.
We're going to do this using an ideal diode at first. And what I want to graph, I'm going to introduce you to the non-ideal diodes. So the whole deal with the diode is this. It'll allow current to flow this way, but no current can flow that way. Everybody remember that, class? It flows in the direction the arrow points, but it cannot flow in the direction there in the opposite direction. So for this one, let's reason this out together. If you look at this right now, until the voltage between here and here is greater than 3 volts, there's no reason for current to flow that way. Does that make sense to everybody, class? I'm going to see this right here. Now, when you start with an input voltage here, I'm going to put input output. This is going to be the input voltage. This is going to be 0. And this is the output voltage. And this is again for an ideal diode. Now, I want you to think about this. Until we get at least 3 volts here, this does not allow any current to flow. Because current, just with this battery, would like to flow this way, wouldn't it, class? But can it flow that way? No. Follow me? So until you hit 3 volts here, the output voltage will not be affected by this. It's as if it's not there. Does that make sense to everybody? So let's do it this way, just so everybody sees this. I'm going to come down here, and I'm going to say this would be Vn here, plus to minus. And I'm going to put 400 ohms here. And then I'm going to put the 200 here. And I'm going to say, if you look at this, until this hits 3 volts, this will not turn on. Does that make sense to everybody, class? So now I'm going to say, well, the output voltage would have to be 3 volts before that circuit, before the diode becomes conductive. Do you all agree with that, everybody? So what does that mean for this voltage? Well, if 3 volts there, what's the current flowing here? 3 over 200, right? So the current I would be 3 over 200, right? And what would the voltage here be? 3 over 200 times 400, right? If that's 400 ohms. Or it's really 3 times 2, right? Or 6 volts. Do you agree with me there, class? I'm going to see this the way I'm progressing. Everybody with me on this? This is an easy thing to see, but an easy thing to miss. Now, that means until the input voltage is 9 volts, the output voltage will be unaffected by that combination. Do you all agree with me? I'm going to see this. So now I come up here and I say, all the way to 9 volts, wherever that is, I know that the input voltage is unaffected by this, or really the output voltage is just what? If that's the output voltage, it's only based on voltage division, isn't it? How many see this right here? So now I can say until we hit 9 volts, V out will be equal to V in times 200 over 200 plus 400 or 600, or it's really V in over a third. Everybody got that? This is all the way up until the input voltage hits 9 volts. Do you all see this, class? Give me a show of hands. I gotta make sure you see this. This stuff will confuse you if you're not clear, if you're not clearly thinking. Now the slope of that is 1/3, so that means at 9 volts, I will literally have 3 volts at the output, right here. And this will be the progression, it'll look like this. Right? All the way to 9 volts. Do you all see that? Now please listen. Everybody got that? Now, some of you are going to see this real easily. It's always this way, and some of them have a hard time seeing it. Now what happens if the input voltage goes beyond that? Suppose it's 10 volts, right? Well, the output voltage would like to be what? 1/3 of 10, right? It would like to be 3.333 volts. How many see that? Right? It would like to be that, but what happens? When it tries to put 3.333 volts here, this thing becomes conductive. Do you all see that? And it limits the output voltage to be 3 volts, no matter what the input voltage is beyond 9. How many see this? I want you to take a good look. So that means this thing stays at 3 volts no matter what I do. You got me on that? And that is something called, it can be used for a regulator. It's something that is a limiter that's limiting the output voltage magnitude. But in the lower ranges, it's linear. Does everybody see this? Now these problems, I don't know what happens, but there's people that struggle seeing these things. They have a hard time reasoning through them. Does everybody see that? Okay. Now, what would happen, I'm going to go a step further just to really pound this one in. I just showed you what it looks like if this is the case. Now what does it look like if this is the case? Instead of 3-volt battery, I make it a 4-volt battery. Now how does that change? If I ask you to graph the output versus input for an ideal diode, what changes, people? Well, now the output voltage is limited to 4, right? Everybody with me? That would be, I wish I had a different color, the marker would work. If this works, I will show you. So now I come up here and I say, if the output voltage is 4 volts, right? Before this turns on, what would the input voltage be? Well, isn't it 3 times the output voltage is the input? Isn't that right, class? Because of that voltage division. This is going to be for voltages less than 4. I have to find out where this occurs. So if this is 4 volts, right? Then my input would be 4 times 3, right? Or it would be 12 volts. Do you agree with that, everyone? How many see this? It would be 12 volts. I'd come out here and I'd say, if I did that circuit, I would look at 12 volts, right? And then I'd say, in fact, my output would track this exactly all the way to 12 volts. And then what happens? Class? No matter what I did, it would still be limited to 4 volts, right? Everybody see that? Give me a show of hands if you do. It'll bother some of you. You'll start wondering about this. This is limiting the output voltage. There's an actual diode that does this. It's called a Zener diode that we'll get to. A Zener diode, until you hit some threshold, it will not allow current to flow. And it's a threshold voltage. So this is limiting the output voltage. And there's a lot of applications for this that we'll get to. But this is for an ideal diode. I'm going to cover one more or 2 more.
Can you explain again why it stays constant out there?
Say again?
Can you explain again why it stays constant?
All right. Suppose, just for a thought experiment, suppose that I wanted to put 4.1 volts here, all right? Just think about this. Well, 4.1 volts would what? Cause this diode to turn on. That diode's a short, it will drive it down to 4 volts. All right? And the reason it can't be that is because that current that's causing that 4 volts there is being supplied through that resistance. And all the voltage drop will be limited to 4 volts there, the rest here. All right, so you get more current as you increment the voltage. The percentage current increases, but the voltage output doesn't. This is a limiter circuit. It's used all the time. I got to tell you, a lot of these circuits, until you see how they're actually, I mean, why that would be really an application you can't appreciate. And I'll try to get to that later. Everybody clear on that with diodes? Now, for the negative values of voltage, I just want you to try to go with me on this. If I talk about minus here. Here, I'm going to have this becoming positive, and I'm trying to drive current this way. Now, what do you know about this? If you try to drive current this way, what happens? Can any go? This looks like an open circuit. So for whenever there's negative voltages here, the output just is 1/3 the input, straight down there. Got that, class? Because the diode has no bearing on that. All right. There's one thing I'm going to tell you for practical purposes that you should know. All these diodes have what's called a maximum breakdown strength, where they're going to block current. All right, the current's trying to flow this way up to a certain value of voltage. When the voltage exceeds maybe 100 volts, they'll break down. They'll literally, the dielectric will have an arc over it. Has anybody ever blown up a capacitor in here? You know what I'm talking about? One person? Capacitors are basically things that prevent DC current from flowing through them. But if you try to put a large enough DC voltage on there, the breakdown strength of the dielectric literally can't stop it. So it'll arc through and you get a sharp arc over. And it's the same thing with diodes. They have a limited amount of voltage they can withstand. And I want to say this for practical purposes. I have done a lot of work where I had to create rectifiers that we talked about, full wave rectifiers. One time we had a 10,000 or 12,000 volt neon transformer that we had to build a full wave rectifier for using diodes. How many remember me talking about diodes being used to get DC? Just raise your hands. If you were here, you did. It took a cycle like this and made it all positive. It's called full wave rectification. Well, each one of those diodes at some point experienced a voltage that was the peak voltage, only it was in the inverse direction. And when that happens, what actually happens is this. You're starting to look at a possibility of breakdown of the diode. It's current in the wrong direction. So the way I get around that, if the diode has a reverse breakdown strength of say 4,000 volts, and I needed a breakdown strength of say 12,000, then I put 3 in series, and they have to be identical, or this doesn't work. And then I would get the breakdown strength. Some of you people will be using diodes. How many here are mechanical again? All right, if you're working with hybrid technology or anything with energy scavenging, like braking systems on cars, you're going to be using diodes like you wouldn't believe. So just try to appreciate what I'm telling you. It's got a practical application. In aero, you probably are too, but I can't think of a direct application because all the UAV stuff is already done. I don't think there's energy scavenging. It's all battery, isn't it? For most of the low weight, and then the heavyweight ones are all gas powered, aren't they, class? Anybody here doing work on UAVs? The aerospace people, I figure, were. No? Okay, I withdraw that comment. I mean, it's a very hot technology right now. And artificial intelligence and all these drone delivery systems that Amazon and Google and the US government are working on. I mean, literally in 10 years, probably everybody here is going to get your mail via drone. You're going to have literally a landing pod somewhere, and the thing's going to fly there and drop stuff. Does anybody know what I'm talking about here? Yeah. Anybody has anybody heard about what's going on in San Francisco and some of these other cities? They're doing this. They're doing it right now. They even have cars. I'm going to throw this in here because this is the last week of class. This is for the Emmys especially. General Ron Burgess is a retired 3-star general, and he was the chief of staff. Now he's got a different title. He does the same job. But he's at the he's up there at Sanford. He told us all, that according to what he's been told, he's a high-level intelligence guy, that in about 5-10 years, your cars that you buy will drop you off where you want, then they'll go park themselves. And when you want to go, they'll come pick you up. Literally, they're going to be autonomous vehicles. How many have heard of this? Has anybody realized that Tesla's got one of those things out there? I have not driven in one of them, but I understand that they are now becoming more and more common in large cities. Are there any down here? Has anybody seen autonomous down here? You have or not? I mean, I'm talking about a vehicle that literally will come pick you up, drive you. The Tesla won't do that, but Tesla will drive for you, yes.
I think the Teslas do that.
The Tesla will drive you on the highway.
I don't know, I haven't been in one. And I'm gonna say this much about Tesla, I don't have the wallet for that.
I mean, the new one's
I mean,
cheap.
the $35,000 one maybe, but the hundred,
But
what was it,
the new truck is super cheap.
124,000 base price? Just out of my range, just out.
What?
I'm telling you, that's gonna be happening. You people are gonna be working
The
on these
Cybertruck
technologies.
starts at
What's happening in
is
front of your eyes
29,000.
is far greater than anything happened in front of mine when I was where you were at.
It's
I saw
supposed to be cheap.
the age of the microchip and a lot of stuff coming in later. You're gonna be on the cusp of AI and a lot of other stuff, yeah.
Like the new Tesla truck.
I don't know. Look, I'll take a Ford F-150, all right? I hope I don't get sued for saying that, but. I tell you, I've never even owned a Ford, but I used to drive one for work.
Dad praises.
I had an old Land Rover Discovery.
He had an F-150.
That thing was a
Now he
tank,
rides
but
an F-150.
everything that could break down electronically, the radio, cruise control did, so. I decided against those.
This is after the 25 or 250,000 thing. If you look at the video of his release, it's on the big screen. He shows
Now,
starting at 29.
Everything else we've talked about, guys, we could go through some
Yeah,
problems.
yeah.
I gave you problems.
It didn't shatter.
I've drawn input to output. They're all based on one fact. The diode is either on or it's not on. That's it. It's an ideal diode. If it's on, it's a short circuit. If it's off, it's an open circuit. It's that simple. That way everything is almost a binary decision on what's going on with the diode. But when you have to do any kind of graphing of waveforms, you have to think through where does it transition from being off to on. And that's the key. And once it's on, it's a dead short, period. Now that's the ideal diode. The real diode's a little different. With real diodes, I'll tell you exactly what happened, and then we'll discuss mathematically how they model. With a real diode, and he gives this in his book, or I can show that to you. I'm not going to require this of you, but the actual equation I have my variation of it, but I'll give you. I'm not going to require you to know this. I've got to use this as a springboard into where I'm going. With a real diode, when you have a real diode like this, and you talk about this being V diode and this being I diode here. If you were to graph I diode versus V diode, the equation that works is I diode is equal to some I naught that has to do with what's called a reverse leakage current that I'll get to, times E to the, and it's going to be E to the Q over KT times V diode minus 1. Now let me explain this. This is about equal to I naught times E to the V diode over 39 about at room temperature minus 1. And he does talk about that. Oh, I'm sorry. Not over, it's times 39, my bad. This is times 39. And you don't have to worry about this, but I'm going to explain why. Q is the charge in coulombs on an electron. The KTK is Boltzmann's constant. T is the temperature in Kelvin. Now, you've probably seen Q over KT in other courses. When if you've had thermodynamics, do you remember this stuff from Boyle's law and things? There were different variations in this, but Q over KT is used over all the time. This is the general equation at room temperature, what it becomes. It's about 39. What it really means is this, don't worry about that, I'm gonna explain how it looks. If I take a look at this diode curve, nothing happens till I hit about 0.6 volts. You can actually put 0.6 times 39 into there, but it's about that for V diodes. And just bear with me on this one, class. Now, at this point, all of a sudden, you're gonna have some very low current here. This will be I naught, and then the current will exponentially start ramping up like this. So, the current starts going up faster and faster, and in the limit, it starts looking like this one has no bearing on it. You follow me on this, class? It's going up at an exponential rate. We never use this equation for any kind of modeling, unless we absolutely have to. We use something called the piecewise linear model, and here's what we do. We say the way a diode's gonna actually operate, this entire thing is gonna have two pieces. One when it's off, and another when it's on. Follow me? Now, this slope here, I'll get to in a second, but that basically is the way we view this. So, it's the piecewise linear model. I want to be absolutely clear about this. So, how do we go about drawing a piecewise linear model based on this diode? And by the way, write this down. These are for silicon diodes. He does not say that. I want to tell you, these are for silicon-based diodes. There's things that are 3,5 compounds like gallium arsenide, there are silicon carbide, there's gallium nitride, there's silicon nitride, there's all sorts of other compounds that aren't pure silicon that are used to make diodes and rectifiers. And they have different curves, all right? There's different models. This is silicon, this is the most common. Has anybody here worked around silicon carbide diodes or transistors at all? In the automotive industry, they're very, very common. That's the reason I'm asking. You have, what was it a lab or in your own work?
No, it was senior design.
You had silicon carbide?
Yeah, for our honor project. We didn't do it with it. We just, it was
You bought it. All right. That's common. So remember, this is only for pure silicon technology. And the way they create transistors is they put impurities in one part of the silicon and a different impurity in the other part, or no impurity at all, and it causes this type of behavior. Just go with it for now. I'm not going to test you on device physics, so I don't feel it would do justice to this course. So, I want to show you the actual model. So what we do with this for the model is this. We say this device is going to look like a battery, and he does it pretty good here. Matter of fact, let me do it this way. When I look at V diode, I diode, this is called a piecewise linear model. Nothing happens until you hit 0.6 volts. This is for silicon only technology. Then, you're going to get something where you're going to have an on resistance here. And this is modeled by just RS as a certain value. This is call it the on resistance. And I'm going to have to show you this. Now, RS technically is equal to, normally it's 25 millivolts divided by the actual diode current. That's the actual RS that's used for an exact model. For us, most of the times, RS is just given as like 40 ohms. All right, follow me in this class? So what this looks like is until you hit 0.6 of a volt, this is called forward bias because current's going in the forward direction. When current going in the direction it's allowed to is called forward. So this is called a forward bias. Until it hits 0.6 of a volt, nothing happens. At 0.6 of a volt, current starts going up, and the slope of this line is going to be related to RS, where this current is related to really the voltage divided by RS. And I want to give you examples of this, because this is, I can see right now you're going to have a lot of questions. And the best way to do that is to show you some actual problems. This is the one we're going to use, the piecewise linear model. So bear with me in this one. I know this seems a little inexact, but just realize from now on, that diode is going to be it's going to look like a voltage you have to overcome, or a battery in the reverse direction. And then when it does that, if it's trying to get current through there, there'll be a resistance in series with it. I'll try to show you this as clear as I can with several examples. So this one. We're going to do this example. This is in the book, if you're wondering. 10.8. And it's this. Our goal is to find the current I is what they want. Now here are the conditions that he gives. Because that 0.6 of a volt is something that is adjustable, what it's going to say is this. It says that it has a forward break voltage or threshold voltage of 0.7 volts. So it's going to say until we get a forward voltage of 0.7 volts, no current flows. Do you follow me on this? Please just understand this. You have to have at least 0.7 of a volt in the direction that would allow current to flow normally before any current flows. So not any voltage, but it has to be at least that, all right? This is an actual diode. It's a very good model. After current starts flowing, then it has what's called, and I call it the on resistance, or a value of RS, or series resistance. R sub S of, for this one, is 10 ohms. What that does is eliminate the need to calculate the resistance for a variety of current ranges. This is going to be given. Let's assume that. This is a very accurate model. So now they want the current that flows here. Now, bear with me on this. If this was an ideal diode, first could current flow the way it's set up, class? If it was ideal. Class? Yes, current would like to flow that way. It's flowing in the direction it's allowed, right? It would flow. Do you agree with me? So for an ideal diode, I want to do it this way, if it was an ideal diode, then the current I would get would be what? If that's an ideal diode, what is it? And it's on, what does the diode look like? Short circuit. If it's a short circuit, the current's limited by 400 ohms, or it would be simply going to be 1.5 divided by 400. And that would be the current if it was an ideal diode. Now, if we use a piecewise linear model, and that's the model we're going to use, and that's what that piecewise linear stands for. If we use a piecewise linear model, which is more accurate, and this is used all the time, I know that now my circuit looks like this. First, current would like to flow, right? We're going to see if it can flow. You with me? So I have 1.5 volts. Now I come here and I say, if it's going to flow, it has to overcome a voltage of 0.7 volts. So I just put in a little battery that's blocking current from flowing. Can everybody see that? Y'all with me? That's preventing current. You got to get beyond that for current to flow. Now, if current can flow, I put in my resistance of 10 ohms, and then my resistance of 400 ohms. And now I want to calculate this current. This is actually a very accurate depends on the diode, of course, but this is very accurate for a standard silicon diode for low power applications. It's got an on resistance of about about 10 ohms. That's a little high. Normally it's about 0.1 or less. And it's got 7 volt, 0.7 volt threshold. You're going to see that all the time. You got to get at least 0.7 of a volt before current. So, well, how much current actually flows? All right, well, if you look at this, how much voltage is actually trying to force current around? I got 1.5 trying to force it, right? But it has to overcome 0.7. So it's 1.5 minus 0.7 would be the actual voltage left to force current around. How many see that? Class, I'm talking to you as I would talk to my students in electrical engineering. This is the way I think about this. So when I look at the current that's flowing, it's going to be 1.5 minus 0.7. That's how much voltage there is after it overcomes the 0.7 of a volt threshold. With me? Now what do I divide it by? Really 410 ohms. And that would be the actual current. It's going to be a lot less than that. Right? It's 1.5 minus 0.7. So it's 0.8 over 410. So just about half, isn't it? That's a real circuit. Instead of forward bias. I'm trying to just show you this. I'm trying to incrementally build on this one. That's how a piecewise linear diode would be analyzed. Okay? In a simple sense. Does everybody understand how I figured that out? I'm going to ask one thing just to make sure. Now suppose this battery, hear me now. If I make this battery 0.5 volts, what happens? How much current flows? 0. Why?
It doesn't
Can't go over 0.7 volts to get it to flow. I just want to make sure we're all on the same page, right? Everybody got that? So just remember that. All right, now, the next step in this little thing, I thought about how do I do that. And I was going to go through the equations where with that exponential equation, in the limit becomes this. But I don't think it would make one bit of difference to you if I did that or not as far as your level of understanding. So now, I'm going to go to the next problem. It's going to use piecewise linear. And you can imagine these can get pretty crazy as far as the circuits that I develop. Mine is not going to be too crazy. Alright, I'm trying to find one that's not going to be too crazy difficult. This is problem 1033, and I'll make sure you have these problems. For this one, now this one's going to be a little more thought-provoking. This is probably 1033. All right, try to follow me on this. I've got a voltage V1 and a voltage V2 here. I've got 180 ohms here. And then I have two diodes that are gonna have the following properties. And I'll give you the configurations. And what we want is V out. So there's a bunch of different things here. I want you to watch this. I want to go through it with you and make sure we can talk our way through this and understand how to go about. The first says this, that V1, this is the first part. V1 equals V2 equals 0, and I didn't say this, but the on voltage, or V forward for this one is 0.6 volts, and RS is 30. So remember, until you get over 0.6 volts, nothing flows. So what they want to do is get the output voltage for this condition. I want you to just think about that. Those are 0 volts, right? What does 0 volts mean? Isn't that 0 volts? Isn't that 0 volts? Follow me the way I did that? Drop in the ground. Now, if that's the case, that 5 volts is between that point and ground. Now, look at this for a second. When I look at this circuit and this circuit are identical, aren't they? In terms of, I should say, from here to here and here to here, that's the same configuration, a diode in series with the resistor, right? They both go to ground, right?
I was just curious, is that 30 ohms or 30 kiloohms?
30 ohms. RS will never be 30 kiloohms. I mean, in any diode. It should be less than 1 ohm. Ideally, you would like it a lot less. 30 is a lot. That's a very small diode. Well, when I look at this, all right, now the next question I ask, well, what's the circuit look like? It looks like I have 5 volts here, then I've got 3K here, right? And then I've got 2 circuits that are virtually identical. Right? You agree with me? Sorry about these pens. I'll try that one. All right, now, hear me now. That's 5 volts, right? Here's a standard way to figure out if the diode's on or off. If you remove both of these diodes, what voltage do you develop here? Just remove them. What would you get? How much current would flow? Answer that. If you cut these diodes out, how much current would flow right there? None, right? Y'all with me? If you pull these out, no current would flow, right? If no current flows, that means that 5 volts would have to be developed there and there, right? How many see what I'm talking about right here? I'm trying to do this rationally with everybody. If you just remove the diodes, what I'm going to see is there enough voltage there to turn them on, for starters. If you take both of these diodes off, you get 5 volts here and 5 volts here. Do you all agree? Give me a show of hands if you do. Yeah, it's going to get at least, there's going to be more than 0.6 volts or whatever that was, right? 0.6 volts. So now if they're both on, and you all agree they're on, I'm going to go through the permutation so you see this. Now what do? Now you're replacing it with the model. And the model is just going to be, and I'll do it right there so you can see it easier. Now I take both of these and I say, since they are on, I replace them with a voltage that's going to, actually it's going to be, it's trying to stop current from flowing, so it's going to be this way, it's plus to minus V forward, which is 0.6. Then I put the resistance here, which was 30, right? 30 ohms. Over here, I put a voltage that's plus to minus 0.6 volts as well. And I put 30 ohms there. And then, oh, I'm sorry, they have 180 ohms in series with both of them. Y'all agree with that, class? I'm replacing the diodes now. They're on. That's what their on model looks like. It's a voltage, it's the forward on voltage, which happens to be 0.6, and it's got a series resistance of, in this case, 30 ohms. Now, the goal is to find this current. So what would that current be? Reason it out. Well, do y'all agree these are in parallel? They're identical circuits in parallel. Give me a show of hands if you agree with that. Here's the way I would do it. There's several ways. This is one. But I'd say if they're in parallel, I know the voltages don't change. But parallel resistances go down by a factor of 2, don't they? How many know that? If they're identical, right? Are you with me on this? So what's the equivalent of that circuit is this circuit. You can take the 5 volts, put in the 3K up here. You don't have to do it this way, but it's easier. Then I go ahead and say that now I'm going to have that same voltage on both of them, which is 0.6 volts. And because these two are in parallel, now I take 30 plus 180 is 210 divided by 2. So now I take my resistance as 210 divided by 2, and I get the current there. That means the current here would be what? You all see what I've done there? You leave the voltages alone because they don't change in parallel. 10 volts in parallel, 10 volts is still 10 volts. You take the resistance and divide by 2. You all with me? Because they're in parallel. How many see this, by the way? Make sure you do. Now, how much current flows there? What would it be? Well, now the total voltage driving current this way is 5 minus 0.6, isn't it? And what? What limits the current? Class? You all see it? You're usually not that shy. 300 at least, or 3,000, right? Plus what? Plus 210 by 2, right? Which is 105, isn't it, class? So I divide this by, and I'll put it down as 3,000 plus 105. And that would be the current if both V1 and V2 are grounded. Does that make sense to everybody? Give me a show of hands if it does. All right, that's the first one. Now, second one, this is the best way to do this, go through every possibility, is V1 is 0, V2 is 5. So now this is my second possibility of what can happen. I mean, is there any questions about the way I did this one? I'm reasoning through it as I do, and I'm telling you. I could write some equations, but there's no need to write several equations because they're reduced to just a couple things in parallel. That's what it reduces to. I'm going to get rid of this. Now part B, or part 2 is V1 0, V2 5. So V1 is 0 and V2 is 5 volts. And now I want I here. Alright. So I'm going to go ahead and put 5 volts here. We're going to reason this out first. 5 volts there, that's still ground. Alright, with me? Oh, actually, they want V out here. What would V out be for this? That would be the current right there, but what would V out be if this is the current, right? Which is what? 4.4 divided by 3105 would be the current. Do you agree with me there? What would the voltage here be? Wouldn't it just be 5 minus 3K times that current? Y'all see that, class? So the actual voltage V out for this one would be 5 volts minus 3,000 times that I, which is 4.4 over 3105, and that would be the voltage V out. For part 2, V1 equals 0, V2 equals 5. You're going to get the hang of this in a hurry. Now, this is what it looks like. Are you with me? That's still grounded. Now, hear me. If this is 5 volts, right? This voltage on this side has to be greater than 5 for current to flow in that direction. Actually, it has to be greater by what? 5 plus 0.6, correct, class? Is it ever going to get there? No, the most voltage we got to work with is 5. Do you all see that? So that means no current flows that way, and all the current flows this way. Does that make sense? Give me a show of hands if you see this. Y'all with me on this one? It can't flow this way because you need at least 5.6 volts there for anything to flow in that direction. All right? I know this will bother some people, but it's the way it is, and you're going to have to deal with it. So if that's the case, we ignore this, and that means the circuit that that is really related to is this. I have 5 volts, then I have 3,000 ohms. There's my V out here with respect to ground. Then I have a single diode, not 2 diodes, and I have 180 ohms. Now, the question is, the answer is obvious, but can current flow that way? 5, I need to get at least 0.6 volts there, can I? Class? Yes, right, it's on. If it's on, what does it look like? Replace the diode with what? A battery that's resisting the current flow, which is going to be the forward voltage, the on voltage, which is 0.6, and the resistance, which is 30 ohms right there. Y'all agree with that? See what I'm doing here? It's on, if it's on, put the battery in, and the opposing current and the resistance, the on resistance. I want to find this current I right here. So now that current I is what? Anyone? Can you all read it? What's the current, guys? In the back. How about the Navy? If you guys can see it, anybody can. What do you get for the current? Well, how much total voltage is driving current this way? 5 minus 0.6. Do y'all agree with that? So it's 5 volts minus 0.6. That's the voltage driving current that way. What's limiting it, class? The 3,000 plus 180 plus 30, right? So that's what? 210 plus 3,000, so it's divided by 3,210 ohms. That's the current, right? Correct? Can't hear what?
0.00137.
Right here? All right. Now, what's the output voltage going to be? Just take a look at it. It would be what? You all see this? 5 minus 3 times that current, right? Because that's the voltage drop here. The rest of the voltage has to go to ground. You all see that? Give me a show of hands if you do. With me. So now I can say the output voltage is 5 minus 3,000 times that I. You want to tell me what that is, sir?
4.995.
About 5 volts. One thing you're going to be taught on this one, the output voltage will be, if these are close to the peak value of voltage in the circuit, will be about this voltage. All right, now the next one for this is say that V1 is 5 and V2 is 0. I bet you all can guess what this is going to be. If V1 now is 5 volts, and this is going to be 3 right here. So V1 is 5 volts, V2 is 0. And I'm after the current I. Now just think about this. If I make this a short and make this 5 volts, will the output voltage be the same? How many think it will? Yes, why? It's an identical circuit. I just took what was V1 and made it V2, right? And took V2 and made it V1. Yes, in fact, that will be the output voltage, and the current will be identical too. So for this one, I'm just going to say V out will be equal to 4.995 volts. Then, I don't know what it was for one. For the final part is V1 and V2 are 5. Now this is important. So now I'm going to say the last part is V1 and V2 are 5 volts. Reason this one out. Yeah.
The VI was actually 0.887.
Where?
For the second.
Right here? Thank you. 0.887. And this is 0.8872. Thank you. All right. What about this one? Both 5 volts. Reason through it. All right. How much current flows this way? Class? How much current flows this way? All right. No current flows, right? Can I do this then? You heard me? How much current flows here? What's the voltage drop here? 0, right? If no current flows, there's no voltage drop, right? How much voltage is from here to ground? 5 volts, all of it. There's no voltage drop. Agree, class? If there's no voltage drop, 5 volts is from here to ground. This is a common way to start seeing things easily with diode problems. That's a simple problem, and I get it. And I was going to do the equations and go through them, but this is probably better. Remember, you're going to get an on, you're going to basically have an on resistance when it's conducting, and you're going to have to overcome a forward voltage. That's the model we use. Okay, guys? All right. I'll give you some homework, and I didn't give you chapter 11 problems, did I? I got to post these problems.